Alright, so in the last video we talked about these things called cofactors and minors, and it's probably a little mysterious what those are at the moment. So I want to give you a definition of them, and then kind of show it to you, and with that we can talk about how we compute determinants in general. I mentioned that we use the first row to expand on in the last video, but we can really use any row or any column, and we'll see how that works out. So let's give a definition first. All right, so definition. If A is a square matrix, all right, so determinants, we can only take these of square matrices. All right. Then, the minor, which we call Mij, of the entry Aij, is the determinant of the matrix obtained by deleting the ith row and jth column of A. Okay, so this is that process that we were kind of doing in all these computations here, where we were deleting a row and deleting a column of that a certain entry lied in, and then we pulled out that smaller determinant, right? That's kind of what we did here. So like this, if we delete the first row and the third column, we get this smaller 2x2 minor here. Okay. Then what is the cofactor? Well, the cofactor, which we call Cij, all right, of the entry Aij, is this number, Cij, which is going to equal -1 to the I plus j, Aij times Mij. Oh, sorry, no Aij, Mij. Okay, so with these cofactors here, we can now write down a way to compute the determinant. Right? So these cofactors, they're basically just the minors of the matrix, but with a plus or a minus in it. Okay, so how do we do this? Actually, first, let me point out, I realized I made a mistake in the last video. These minors, or sorry, these cofactors don't include the A's. That's a mistake on my part. I will point that out. Okay. So, what do these minors and cofactors have to do with the determinant? All right. Well, first, before we get on with that, let's do some examples of computing minors and cofactors. All right. So here, let's say we have the matrix A equals 103 minus 214, 617, let's say. All right, so here's our matrix A. All right, so there are 9 minors of this and also 9 cofactors. Right, every entry has a minor and a cofactor. So let's say we look for the if we do the I equals I don't know, 2j equals 3 entry. All right, so the 2, 3 entry. All right, then M 2, 3, we obtain this from the matrix A by looking at A and say, okay, row 2, delete that, column 3, delete that, and then whatever's left over, we make a determinant out of that. So 1, 0, 6, and 1. Right? And then we just do this determinant. So this will be 1 times 1 minus 0 times 6, which is 1. All right. Now how about the cofactor? All right, the cofactor C23, this is negative 1 to the 2 plus 3 times M23. So this is negative 1 to the 5th times 1, which is negative 1. All right, so this is the 2, 3 cofactor. Let's do one more. Let me just copy this again. All right, let's see. Let's do the minor M33, right? So here, if we're doing M33, we want to delete the 3rd row and the 3rd column, right? I used 3 in the last one. Let's change this to a 2. A 1. Let's change it to a 1. All right, so M31, we would delete the 3rd row and the 1st column. All right, so now we have our 2 by 2 up here in the corner. And so that determinant would be 0, 3, 1, 4. All right, so we compute this. 0 times 4 minus 3 times 1. That's negative 3. And then the cofactor, C31, is going to be negative 1 to the 3 plus 1 times M31. So that's minus 1 to the 4th times negative 3. And that's just going to be negative 3, right? Because negative 1 to the 4th is 1. All right. So now look at what we have. Right? So this is just a way that we can sort of break a matrix into these smaller determinants. Now, why is that kind of thing useful? Well, as it'll turn out, we can use that to compute the determinant of a matrix. All right, so this is, let's see, determinant of a matrix. Okay, so if A is an n by n matrix, right? N here needs to be greater than or equal to 2. Otherwise, we can't really do this minor process, right? It doesn't make sense. So N has to be at least 2. Then we have a few ways we can actually expand out this determinant. So if you think about how we computed the 3 by 3 determinant, what we actually did was we did A11 C11 plus A12 C12 plus dot 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 A1n C1n. All right, so we took all of the cofactors from the top row, multiplied them by the entry they're the cofactor of, and then we added them up. All right, so this right here would be a first row expansion. All right, but there's no reason we have to only do it that way. All right, we don't only have to use the first row. We can also use the ith row. So we can do AI1 CI1 plus AI2 CI2 plus dot 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 plus AIN CIN. Right? This here would be an ith row expansion. Right? So remember how we went through the entries in the first row before when we did the computation? We can use any row and just move through the entries, take that entry, multiply it by its cofactor. All right? But we don't even have to stick with rows. We can do it with columns as well. A1J, C1J, plus A2J, C2J, plus dot dot dot, plus ANJ, CNJ. Okay? This here is the jth column expansion. All right? So there's a bit of a shortcut for kind of understanding this cofactor business here. So hopefully the minor stuff makes sense. The sign of the cofactor, how does this work? So sign of the cofactor. All right, so of course we can always just do -1 to the I plus j. But it's kind of neat to think about a pattern that comes out of this. So for 2x2 matrices, it's always plus, minus, minus, plus. Right? For 3x3, plus, minus, plus, negative, positive, negative, positive, negative, positive. Right, so it always forms this kind of checkerboard pattern, if you will, of pluses and minuses. So when we're computing the cofactor of, say, in a 4x4 matrix, if we're doing the cofactor C32, right, we would look at this pattern here and say, oh, 3, 2, that's going to have a minus sign. So we compute the minor, and then we put a minus sign in front, right? And that makes sense because 3 plus 2 is 5. In other words, if we take the position we're at, ij, and we add them together, if it's odd, we get a negative sign. If it's even, we get a plus sign. So let's do another determinant here, but of a much bigger matrix. And let's really see why this idea of cofactor expansions is actually quite useful. Right. So example, let's say A is, let's see, what do we have here? All right, let's do a 5x5. How does that sound? All right, so we got 5, 0, 0, 0, 0, 2, 1, 0, 0, 0, 0, 4, 2, 3, 0, 0, 3, 6, 4, 0, and -2, 2, 3, 1, 2. All right, so we got this big 5x5 matrix here. How do we do the determinant of this thing? Right? This is really where the power of being able to choose any row or column comes in. All right? So if we look here, think about how these determinants are written out. We're always multiplying by the entry. It's always entry times cofactor. So If we pick a column or a row with a lot of zeros, then we're going to get a lot of zeros in the determinant. So here, let's choose to expand upon this first column. Okay. So how is this determinant going to work out then? So the determinant of A, it's going to be this first entry. Okay, so 5. All right. Now this is in the top left position, so it's going to get a positive sign for the cofactor. All right. And then the minor is going to be the 4 by 4 matrix created when we delete that row. Right, so we have 1, 0, 0, 0. Put a 0 here. Okay. 4, 2, 3, 0. 3, 6, 4, and 0. 2, 3, 1, and 2. All right. But then look at what's going to happen next. So once we're done with that, all the other entries are 0. So we don't even have to bother attempting to compute those determinants, because since all of these are 0, it's just going to be 0, 0, 0, and 0. This is the benefit of being able to use any column or row. We pick the one that has the most zeros in it, and then things go away. All right, so now our question, though, is, well, we still have this 4 by 4 we have to compute. How do we do that? Well, we do the same thing. So we now have 5 times, we want to compute this determinant. So we can pick a row or a column, it doesn't matter. Let's pick a row this time. And again, it's always a good idea to pick the row or the column with the most zeros in it. All right, whether that be a row or column. Here it doesn't matter. Here we have a column with 3 zeros. Here we have a row with 3 zeros. So either one is a good choice. And again, we could technically use any of these rows or columns, but it's always a good idea to pick the one with the most zeros. All right, so let's expand upon this bottom row here. All right, so now we have 3 zeros. So this starts out with 0 plus 0 plus 0. Okay, and then plus 2. Now here's the question. Is the sign of the minor for this last entry positive or negative? All right. What we can always do is say, okay, this is the 4, 4 entry. 4 plus 4 is even, so it should be positive. But we can also do plus, minus, plus, minus, plus, minus, plus. You can just use that checkerboard pattern. All right? So it's going to be a positive one, a positive minor here. And then if we get rid of this column, we now have a 3 by 3 left. So I mentioned earlier that determinants are an inductive process. This is what I mean. We took a 5 by 5 determinant and we cut it down into 4 by 4, or into a 4 by 4. Usually it would be a few 4 by 4s. Okay, and then we take the 4 by 4 and we cut it down to what would, again, usually be a few 3 by 3s. Okay, so now that we have that, let's simplify what we have a little bit. So this is 5 times 2 times this determinant. All right, now we're hopefully a bit comfortable with computing 3 by 3 determinants by now, just using the first row, but there's no reason to just stick with the first row, right? We can keep doing this process here. So if we continue this process, we have 5 times 2 times, well, if we look at this first column here has the most zeros in it, right? So this is a good choice. Right? So we have 1 times the cofactor of that entry, which is this. Right? So 1 times 2, 6, 3, 4. Right? Okay, and then look, these next two are both 0, so plus 0, plus 0. Right? And then now we have 5 times 2 times 1 times this determinant. Right? Now, once we're down to a 2 by 2, there's no point in doing any expansion anymore. This is just a simple multiplication. So we have 5 times 2 times 1 times 2 times 4, which is 8, and then minus 3 times 6, which is 18. So this is 10 times minus 10, so negative 100. And there's our determinant. So again, it's an inductive process. We start higher up and we just keep cutting down the size of the matrix until basically we get 2 by 2s. And then that's that. Right? So hopefully that makes sense. I know this is a bit of a long video. Probably should have done this example in the next one, but hopefully it's not too bad and it all makes sense. And we'll see you for the next one.